You can see two of my kids here. In my spare time, I write small poems about pictures of my kids when I have the time. And at some point, I was reminded of the story of the Babel Tower. Most people probably know it. It's a famous story that ends with everyone being forced to speak different languages, unable to communicate. It's one of these stories that teach us that communication is paramount, like everywhere. And I think this applies to Linux as well. I'm not talking about the mailing list etiquette. No, I'm trying to talk about Linux IPC, about how we communicate between processes locally. When we talk about communication on Linux, we have these like this one spectrum with two ends. On one side, we have a lot of current research in making programming languages work well with thread communication, making it as easy as possible, as performant as possible to talk between threads, synchronize between threads. On the other hand, we have networking protocols. The entire cloud spends billions just to make it easy to scale up your workload. And in between these two, we have IPC. And when we talk about IPC, like, it's usually a big word for lots of things. But what I want to focus on today is the small part in between, where we have machine local communication, but it's not shared memory. So we are communicating over some other transport. Over the years, Linux IPC has developed, and especially we have many different encodings, many different libraries and styles that have evolved. But the transports, they didn't change. We still use basically the same transports that we used 30 years ago. And my question is why? Why do we do that? Did the competition leave us behind? Did they do something else? Or is there just nothing that people want? Are we just always stuck with what we had 30 years ago? I want to do a quick tour and take you from cold boot to browser on a standard Linux system that most of us know, and just shortly look at what kind of IPC we have on these systems. I don't want to do a deep look into each individual one, just enumerate them and try to categorize them afterwards. When we start a system, the first thing we see is UEFI. We usually don't think of UEFI of using IPC, but if you look at UEFI in detail, you can have multiple images at the same time, and these communicate over UEFI protocols. They implemented as direct calls on most systems, but conceptually, they are symmetric calls like on an IPC system with a rendezvous-based communication. So the receiver and the sender both need to arrive at the same at a well-defined location in their code for that communication to happen. But if we leave UEFI, we get to the most basic IPC on Linux systems, which is standard input, standard output. It originated, of course, in Unix systems, and we still do it these days. We use it for pipelining on terminals. We use it mostly for logging these days. But if you boot up a Linux system, you still get all these messages. These are sent to standard output on Linux. Standard output is an asynchronous communication. Usually, like how it's implemented, it is buffered, but it's used with flow control. So you usually have a blocking calls, at least like how the terminal pipelining was meant to be used. And it's tightly integrated into the flow control of your application. Like if your output pipe is closed, you usually get a signal that terminates your application. And it uses string encoding. So we move further on, we still are in early boot. We see some things like UDEF. UDEF, again, uses its own IPC protocol. It's the only one that uses netlink as a transport in user space. It sends simple key value string arrays over this netlink passage, and its most profound feature probably of the IPC is that you can use Bloom filters to filter all of these messages on the system and just see the ones you're interested in. Again, UDEF is message-based, it's not stream-based, it's an ordered multicast system, everything is on a single bus instance. Also, it's kind of not used by anyone else, like this IPC system used by UDEF didn't really take off, and I would bet that nobody would design it again this way, but still we're using it on all systems up to date. Then we have some more obscure things that are running on your early boot system. It's something called systemd ask password. This is used when your system is still not full up, but you need to somehow get a password from your user. You need to get input without having a graphical system or having keyboard initialized. And the way this works is it's quite creative. The dbus is not up yet, so they have to do something else. When you want to ask the system, the user for a password in early boot, you create a socket where you want your password, like your reply, and you bind that socket to the file system. And then you create an ini file where you write the path to your socket and other information as well. And then you place that ini file into some path in /run, and you hope for somebody to pick it up, to ask a user for password via whatever means possible, and then send you back that information, and you unlink that ini file. Like, it's kind of ridiculous if you know like how other IPC systems work, but we have that because at the time we didn't have an alternative that we could do in that situation. But it kind of shows the creativity involved in a lot of the IPC systems that we have on Linux. From there on, we now have an initialized user database. The next thing that is available is dbus. Most of you probably know dbus. I'm not going into details here. dbus is provides you an asynchronous communication based on messages over Unix domain sockets. Has a custom binary encoding, and I think the biggest benefit of dbus is its rich ecosystem. It has lots of debugging utilities and allows you to introspect the system and debug whatever's going on. I still think it's a very complex system and rather slow because it has this single broker instance where every method goes through, but it's still, I guess, the most popular general purpose IPC that we have. And then there are more, like we have the journal and WPA supplicant that just have string arrays over Unix domain sockets. We have Wayland and Pipewire that have binary protocols over Unix domain sockets. And then we have Warlink or Docker that even do like JSON or REST over Unix domain sockets. And all this is involved in early boot. These are all different kind of IPC systems. And then at some point we end up in the browser. And the browser basically says, thank you system for bringing everything up. Now I take over. And they do everything on their own. Why do they do that? Because they need to be cross-platform, of course. They have a hard time finding APIs that they can use on all different platforms. So what does Chrome and Firefox do? They have Chrome Mojo and Firefox IPDL, where the latter is actually implemented on some things of Chrome Mojo. And this is an IPC system that provides, again, similar to dbus, asynchronous messages over Unix domain sockets on Linux. Has a custom binary encoding and this rich interface definition language, which I have a short example here. And this is tightly integrated into the browser. They use it for everything. Every inter-process communication in the browser uses this. And this short overview over the boot sequence on a Linux system these days, it shows that we have like this rich set of many different IPC systems, and they have many different encodings, they have many different libraries, many different features they provide. And I think encoding matters a lot. Like, it makes sense to discuss whether we want to use JSON to encode something or whether we want to use a binary encoding. But I want to ignore that part. I don't want to talk about the encoding. I want to look at what is underneath that. I want to categorize all these systems we have now based on the transport they use. And if we do that, we will realize a lot of these are based on networking ideas. If we look at REST and JSON over Unix domain sockets, like Docker and Warlink do, these are clearly like technologies that originated in networking and are just tunneled over a local socket. We have what Pipewire and Wayland do is they have binary encodings over Unix domain sockets that like conceptually originate, I guess, in X11, which was, again, a remotable protocol. So whatever we do in early boot, this is basically networking. We don't take any advantages of local features of our system, with a few exceptions. And I've listed them here. The journal, for instance, allows you to pass memFDs instead of just sending log messages directly. Wayland allows you to share DMA buffs. again, via SEM writes on Unix domain sockets. But these are optional extensions to the protocol. They're not mandatory. You can do things differently, so the protocols are still remotable. And lastly, like the one exception is things like systemd password that just do crazy things locally using all kinds of local features. But I would argue these are not really like nice to use for a general purpose sense. So are we just doomed to use networking protocol on local systems? Maybe there is no place between threading APIs and networking protocol, because clearly nobody makes heavy use of any of these things. And additionally, like what happened to all the different ideas that we had over the years? Like if you look at the kernel and at the POSIX message queues, for instance, at the FIFOs, the real-time signals, anything that is in the kernel IPC directory, like any API they implement, nobody uses. This is basically just Unix domain sockets, maybe pipes. So it feels like there's just nothing that we have used. So in the second part, I want to look at what do others do? Were we left behind? Didn't we just miss out on something? Microsoft Windows, what do they use? Everybody knows that they have the component object model, COM and RPC. These are the most significant RPC systems on Windows. But they're underpinned by something called LPC, ALPC. It's a local procedure call instead of remote procedure call. It's a system call provided by Microsoft Windows that looks very much like normal socket-style communication on Linux, where you have like a TCP model, where you have a listener socket, you create a listener socket, you bind it to some well-known path, other clients connect to it, you accept that connection, and then you get another socket that you use for peer-to-peer communication to that peer. It looks exactly like TCP communication. And I guess that's where it originated. But it has this extensive metadata transfer possibility. So you can add all kinds of metadata as a sender or request it as a receiver, and you get it authorized by the kernel and validated by the kernel. So you can get like SIDs, you can get like the equivalent of user IDs on Windows, and task information. You can get shared memory passed along, and so on. The problem with that is it's not exposed in the Win32 API. Like it's not a public API of Microsoft Windows, even though it's likely stable and a lot of people use it directly, but it's not actually part of it. Second part, macOS. What does macOS do? macOS uses Mac ports, like something that originated in the Mac microkernel. Mac ports is a capability-based system where you say you create this thing called a port, and you initially get a set of rights for that port. And now you can share these rights with other processes. And these rights are, for instance, I can receive messages on that port. I can send messages to that port. There are some more rights, but effectively how it is used is you create the port, you retain the receive rights, and you give send rights to other peers. And everybody who has a send right can now send messages to your port, and you receive it on that port. There's a very basic, very simple, very trivial technology, but that made it so successful. Like it's used all over the place. If you take XPC, which is the exposed IPC on macOS or iOS, it's based on Mac ports. And IOKit, the driver framework, or AppleScript, the event framework, everything based on Mac ports underneath. Mac ports it's a unidirectional system, so you only send messages in one direction. And it has one FIFO per port. So when you have multiple ports, every port has its own queue. You get no ordering across these ports. But again, this was a very cheap system. The idea was that you can use it for everything. Whenever you have any object you want to represent to other peers, you create a Mac port for it, right? And this was so popular, like it was used all over the place, that Solaris, when they created Sun, when they created Solaris, they wanted to take that as well. They created something called Solaris Doors, which extends Mac ports, but tries to use it for really everything. And they realized, like, if you want to use it for system calls, it's still slow. It's still asynchronous communication. It's still a lot of state tracking. and they optimized the hell out of it and tried to say, yeah, we want everything to look like a Mac system call. And they succeeded. They made sure you can use it like for a few, like less than 1 kilobyte of information very fast to do like a Mac call for system calls. And everything on the system suddenly looked like these Mac ports. And this went on further, that at some point something called Open Binder emerged, which kind of inspired by Solaris doors, because it takes the Mac ports model, the capability-based model, and made it bidirectional for fast bidirectional operations, and added strong support for synchronous system calls. And Android they don't use the Open Binder code, but they use Binder internally heavily. And to understand where that comes from is that it's like 2005, 2006, where we had these small ARM machines with a single core, and you try to run an operating system on them for your phone. You wanted them to be like interactive, low latency. If you do something like your background tasks, they can wait. You want like the interactivity to be the immediate response. So what they did is they tried to optimize for synchronous calls a lot. And if you do a call on Binder to another process, you can actually like immediately when you do that call, schedule in that other process. This will out of order execute your synchronous call, queue reply, immediately jump back to you. It will use your time slice in the scheduler if it can. And this actually worked. Like you could use like Android phones back then, and it was fine. It was fast. You couldn't do that with Mac ports. It would never work that way. But Open Binder did more. They did a strict split. They removed this concept of writes. They said, no, we don't care for writes. The only thing you care for is you want some end where you can receive messages and one end where you can send messages. A node is your object. That's where you get your messages and you can dispatch them. And you get references, and references you pass around. And this is like this split that is still there today. And it worked. Like they got rid of this entire concept of having these different writes and just say, no, we only pass around references, and they give you the right to send messages. And send messages means invoking something on that node. They went one further. They introduced shared queues. So you can have many different nodes, but only one incoming queue. Meaning if different peers send different messages, you get them ordered in a single queue. You don't have to dispatch several different queues, and you don't know which order they were. You don't starve one queue just because you're dispatching another one. And they added lifetime notifications, so you suddenly no longer have to multiplex the operations on a single node, but they encourage you to create a different node for every different single small object you have, because they are so cheap, and you get notifications when a node goes away, when you create a new one, and pending calls are like automatically aborted if like the node you call on goes away, and things like that. And later on, of course, they improved a lot the asynchronous operations for Binder, allowing you to run on multi-core machines these days, and reducing all this contention when it was optimized for synchronous calls. There's some more honorable mentions of other operating systems that I don't want to get into, but SEL4 is the only synchronous rendezvous-based IPC system out there, but it's not used for like these highly complex systems that Linux is used for. The Zircon kernel is also very much Mac ports inspired. I don't think they're conceptually that big of a difference. There's a Microsoft Midori research project. It was really interesting to read about, where they also try to use something like Mac ports, similar to Binder in a sense, on a Microsoft system. And there are third-party, high-level IPC systems like the E language or Cap and Proto, which try to use cryptography to get these capability-based systems on top of a network. So this is my last slide. What are my personal highlights of these IPC systems? Like, did we, as Linux developers, miss out on something? And I think what Solaris Doors did for their system calls is really nice. Having a way to represent a system call in the same way as you do a call to a different process allows you to virtualize your system without like depending on specific calls that you do, depending on being a system call into the kernel. And nobody else did it in a way they did it. But I think that's sad. It's something we should maybe look into and maybe revive. Binder lifetime notifications allow Android to use binder like across the entire system for everything they have. The e-order is something the e-language does, where they say, we want to order messages like something that is close to causal ordering. So if multiple different messages are sent over a network, the first message, you still get causal ordering. They're not reordered if they end up in different queues. This is very strong. Dbus, for instance, does that on Linux. Dbus gives you a global order because it's only a single point where every message goes through. But they do something similar, but without the contention on a single point. And again, I think this is really, really something nice that we should replicate, because ordering problems are really hard. And if you get them for free on a local IPC system, it's really, really nice. But as a last thing, two things that I did not find anywhere is actually resource accounting. Like all of these systems, you can easily explode by just sending many messages and filling a FIFO queue of the receiver, and you dust them. This is all across the board. The exception is SEL4, because if anybody knows how L4 works, it's very different. But none of the other ones use any kind of sensible resource accounting. And there's little support for first-class decoupling of libraries, where you want to say, if you're a library author, you want to be able to use an IPC system of your application without interfering with that application. You don't want to duplicate it and be like at this heavy second layer, but you want to reuse it, but not mess with whatever state that application uses in that IPC. I'm very much interested in what you have experienced with IPC. I'm a maintainer of Dbus Broker. I maintain a Dbus instance. I spend a lot of my time looking at what people do with their IPC and systems, and a lot of people are not happy with the situation. And we noticed that the big scope, the many different implementations that exist and that are used on Linux show that there's no agreement. And I would love to hear from you. I'm around the next 2 days. What you would love to see in IPC, which of the other systems you have used, which one you liked working with. Yeah, if you have any questions, just ask me.
If you have questions, yeah.
So you mentioned that there are many people not happy about the current situation. What are the common problems?
I think one of the current problems is that Dbus was an approach where we, with different desktop environments, tried to cooperate and get this one system that they agreed on, and it worked fine for desktop environments, and it was adopted by more and more lower layers. But Dbus always has this problem that you can't use it ad hoc. Like, you have to connect to this global bus, you have to figure out where it is, you have to find it, and then on top, Dbus is rather complex. It has a binary encoding nobody else shares. You can't use it easily from a script. You can't just send a JSON message you create in your Bash script or in your Python script. And that, yeah, kind of makes people hate this concept of how it is set up. And the other problem is it's slow. It has this single point where every message goes through. It provides a global order, which is nice, because you can argue based on the ordering of messages you see in your debugging that everybody saw messages in that order. But it also means if you have a multi-core CPU, your boot is slowed down. You have this one bottleneck where you have this contention.
Yeah, the last question.
What's your explanation for the current state? Like, how is it possible that the general purpose Linux system, I'm not talking about Android, for example, was able to survive so long without foundational, always there, use for everything IPC?
It's hard to answer, I guess. It's definitely nice to see that every other system that's popping up, the first thing they do is they explain the IPC system. It's really lovely to see, and on Linux you don't have that, as you're saying. I think it's a hard problem, like it's not easy, and there's a lot of discussion to be had about things that don't necessarily affect the transport layer. Like if you try to convince DBus enthusiasts about using JSON, they will cry about giving up their binary encoding. At the same time, like everybody who has argued in favor of something that is not JSON or some string-based encoding has argued based on performance. And it's really hard to then try to agree on something if that's the discussion people are having. I don't know. I think it just worked. And giving everybody the possibility to do their own thing is not bad. Like it's hard to agree on something then, sure, but it kind of shows also what people come up with. It's a great source of inspiration for a lot of ideas.
Okay, thank you very much. We're running out of time. Thanks again, David.